everyone, welcome to Trigonometry. My name is Elaine Tintoni and I'm the lead online math instructor at ICC. I'm going to be going through this entire trigonometry course with you. Today we're starting off in section 1.1, which is all about angles. And in this section we'll pick up some basic terminology, we'll talk about degree measures, we'll talk about standard position, and also coterminal angles. So here we go. Let's start with a little basic terminology. So an angle consists of two rays in a plane with a common endpoint. And you can see that here. We're all familiar with angles, so this is nothing new to anyone. The two rays are the sides of the angle, and the common endpoint is called the vertex of the angle. An angle's measure is generated by rotation about the vertex, and the ray in its initial position is called the initial side of the angle, and the ray in its location after rotation is called the terminal side of the angle. So we'll use those terms a lot, the initial side of the angle and the terminal side of the angle. Now a positive angle is whenever the rotation of the terminal side is counterclockwise, like you see here. This would be the initial side of the angle, the rotation is counterclockwise, and this is the terminal side of the angle, so this angle would have a positive measurement. And a negative angle is when the rotation of the terminal side is clockwise. So here you see an angle where the two sides are in the same position as the other angle, but for this second angle the rotation is clockwise. So this angle would have a negative measurement, whereas this first angle that rotates counterclockwise has a positive measurement. Now let's talk about degrees. The most common unit for measuring angles is the degree. And if we start an angle with its initial side right here, and the terminal side rotates all the way around so that it stops where the terminal side lies exactly on top of the initial side, then that is a complete rotation, and that would be an angle whose measure is 360 degrees. Now, as you probably already know, some angles are classified by their measures. An acute angle is an angle whose measurement is between 0 and 90 degrees. And I want you to pay attention to this symbol right here. This is the Greek letter theta. This is lowercase theta. And this is the typical symbol that we use to represent an unknown angle in trigonometry. It's not the only symbol by any means, but it is very common to see theta represent an unknown angle, just like it's common to see x represent an unknown value in algebra. And the way that you'll write this symbol is you'll make kind of an O, but make sure and put a loop through the top of it like this. So this is the lowercase of the Greek letter theta. But as you can see, an acute angle has a measurement between 0 degrees and 90 degrees, not equal to 0 degrees or 90 degrees, but between them. A right angle has a measurement exactly equal to 90 degrees. An obtuse angle has a measurement between 90 degrees and 180 degrees. Again, not equal to either one, but between them. And a straight angle has a measurement exactly equal to 180 degrees. And you can see why. Because the initial side and the terminal side form a straight line if the angle is 180 degrees. Now I want you to be a little bit careful with your terminology here, because I think in the lower grades sometimes people get used to saying an acute angle is any angle that's less than 90. But we can't say that here, because notice that the lower bound is 0 degrees. If we just say less than 90, well, that includes all the negative angles. And the acute category does not include the negative angles. Notice it only includes angles between 0 and 90 degrees. And again, with the obtuse angle, I think we get in a bad habit sometimes of saying an obtuse angle is any angle bigger than 90. But again, that's not the case, because notice that an obtuse angle has to be between 90 degrees and 180 degrees. So we can't just say bigger than 90. We need to say between 90 and 180 degrees. Now let's talk about complementary and supplementary angles. Complementary angles have a sum that is 90 degrees, and you'll usually be able to look for the right angle indicator here, and that indicates that the sum of these two angles is 90 degrees. And supplementary angles add up to exactly 180 degrees. So two angles are complementary if their sum is 90, and two angles are supplementary if their sum is 180. And here's our first example. So example 1 says, for an angle measuring 40 degrees, find the measure of A, its complement, and B, its supplement. Now I know for an angle as simple as 40 degrees, you can do this mentally, but let's make a good habit of how to write down the work. So we know that if the relationship is complementary, that means that our unknown angle and our 40-degree angle have to add up to 90 degrees. So I'm going to use theta for my unknown angle. So I'm going to say theta plus 40 degrees equals 90 degrees. So that's what it means for two angles to be complementary. And we know that to solve this, you would subtract 40 from both sides. So I won't show that here the same way you would in algebra, but you could if you wanted to. Just subtract 40 from both sides. And so then we would have theta equals 90 degrees minus 40 degrees, which we know is 50 degrees. And sure enough, 50 plus 40 is 90. And now let's do the same thing for the supplementary angle. So if the two angles are supplements, that means our unknown angle plus 40 degrees has to make 180 degrees. And same thing, to isolate the theta, we subtract 40 from both sides. So then we would have theta equals 180 degrees minus 40 degrees, so theta would be 140 degrees. And here's example 2. It says find the measure of each marked angle. So we have two angles that together are forming a right angle, and that means these two angles are complementary. In other words, their sum is 90 degrees. So we can start by writing 6x plus 3x equals 90 degrees. And then just using basic algebra, 6x plus 3x is 9x. So now we have 9x equals 90 degrees. To isolate the x, we divide both sides by 9. And of course that gives us x equals 10 degrees. Now we're not finished yet because the question said find the measure of each marked angle. So now we need to say 6 times x is going to be 6 times 10, which is 60 degrees. And for the other angle, 3 times x is going to be 3 times 10, which is 30 degrees. And then just for a check, we want to make sure that our two answers do add up to 90 degrees. And you can do that mentally, of course, but I wrote it down here. 60 degrees plus 30 degrees is 90 degrees. And here is part B. For example 2, it says find the measure of each marked angle. So from this diagram, you can see that the 4x angle and the 6x angle together form a straight line, which means that these two angles add up to 180 degrees. So we can write the equation 4x plus 6x equals 180 degrees. Combine terms on the left, 4x plus 6x is 10x. So now we have 10x equals 180 degrees. To isolate the variable, we divide both sides by 10, and that gives us x equals 18 degrees. And now we need to use that 18 to figure out the measurement of each individual angle. So we'll say 4 times 18, and we know that that's 72. And for the other angle, 6 times 18 degrees gives us 108 degrees. And then just to double check for ourselves that 72 degrees plus 108 degrees does add up to 180, and it does. So now let's talk about degrees, minutes, and seconds. We don't think of it very often because degrees are already very small. You know, there are 360 degrees in a full rotation, but the degrees can be divided into parts, just like an hour can be divided into parts. We divide hours into minutes and seconds. Degrees can be divided into minutes and seconds as well, and it works the same exact way because the system was developed by the same set of folks. It was the ancient Babylonians that came up with this system, and we still use it today. So 1 degree can be divided into 60 minutes. If you wanted to write that in symbols, you would say 1 degree is equal to 60 minutes. And the symbol for minutes is like an apostrophe or like a single quote. So 1 degree is 60 minutes. Or you could turn that around and say that 1 minute is a 60th of a degree. But just like an hour of time contains 60 minutes of time, a degree of rotation contains 60 minutes of rotation. Now we can divide minutes into seconds. So just like it does with our time system, 1 minute equals 60 seconds. And the symbol for seconds is 2 apostrophes, or it might look like a double quote. So if we want to say 1 minute equals 60 seconds, we'll write 1 minute with the single apostrophe equals 60 seconds with the double apostrophe. Or if 1 minute is 60 seconds, that means 1 second is a 60th of a minute. Now let's see if we can make the connection between seconds and degrees. So if 1 degree equals 60 minutes, and there are 60 seconds in every minute, then 60 times 60 is 3,600. So that would mean 1 degree is 3,600 seconds, because every degree contains 60 minutes and every minute contains 60 seconds. So we could write 1 degree equals 60 minutes, and that equals 3,600 seconds. Or if we want to go the other way, we can say 1 second is a 60th of a minute, and every minute is a 60th of a degree. So a second is 1/3600th of a degree. So just try to imagine how tiny, tiny, tiny a second of rotation would have to be. So now let's look at example 3 together, and we're going to talk about how to convert between decimal degrees and what we call DMS notation, or degrees, minutes, and seconds. So part A says convert 74 degrees, 8 minutes, and 14 seconds to decimal degrees and round to the nearest thousandth. So to do this, we just need to remember that 8 minutes represents part of a degree and 14 seconds represents part of a degree. We've already got these 74 degrees here, so let's go ahead and write down 74 degrees. Now these 8 minutes represent 8/60ths of a degree, because we know that there are 60 minutes in a degree. So each minute is a 60th of a degree. So these 8 minutes are 8/60ths of a degree. And then for the 14 seconds, we just remember that there are 3,600 seconds in every degree. So these 14 seconds represent 14/3600ths of a degree. And now we can just add degrees. So on your calculator, 74 plus 8 divided by 60 plus 14 divided by 3,600 equals 74.13722222, and that's in degrees. Now they asked us to round to the nearest thousandth, so the third decimal place will be our last digit. So to round to the nearest thousandth, we look at the fourth decimal place. If this number in the next position is 5 or more, then the 7 goes up. In this case, the next digit is a 2, so that's not big enough to make the 7 change. So when we round, we will have 74.137 degrees. Now I've used the squiggly equal mark here to show that rounding has taken place. That won't matter at all for you in Math Lab, but it is good practice when you're writing that if you've done any rounding, try to remember to use the squiggly equal mark. That means approximately instead of exactly equal. And in part B, we're going to be converting the other direction. We're going to start with 34.817 degrees, and we're going to convert that to degrees, minutes, and seconds, or DMS notation. So we know that we've got 34 whole degrees here. So let's go ahead and write down our 34 whole degrees. And then this 0.817 represents part of a degree. So I'm going to write 34 degrees plus 0.817 degrees. Now the trick here is to convert this partial degree into minutes. Now we know that there are 60 minutes in a degree, so if I want to convert these degrees to minutes, I can just multiply by 60 minutes over 1 degree. So the degrees would cancel out and leave our answer in minutes. So this 34 degrees is separate, and all I'm going to do on my calculator is 0.817 times 60, and that's going to give us 34 degrees and 49.02 minutes. See, we converted this partial degree into 49.02 minutes. Okay, now this partial minute, this 0.02 of a minute, represents some number of seconds. And so we're going to separate this answer now into 34 degrees and 49 minutes and 0.02 minutes. And we want to convert this partial minute into seconds. So we know that there are 60 seconds in every minute. So we're going to multiply this partial minute by 60 seconds over 1 minute. So in this case, the minutes cancel out, and our answer here will be left in seconds. So again, we don't need to consider this when we go to the calculator because this is already in degrees and minutes. So we'll just have 34 degrees and 49 minutes, and then 0.02 times 60 gives us 1.2 seconds. Now, before we write our final answer, it's important to keep in mind that a part of a second is so very small. Seconds are already tiny, tiny, tiny. And so a part of a second is hardly worth considering at all. And so normally what they'll tell us in the instructions, although you can't see it here, I did not type it here, but normally in the instructions, MyLab will tell you round your answer to the nearest second. And so here where we have 1.2 seconds, we would round that off to 34 degrees, 49 minutes, and 1 second, because that 0.2 of a second is not big enough to make the 1 second round up to 2. Okay, so that's our final answer. And you might just want to make yourself a note that we almost always round degrees, minutes, seconds to the nearest whole second, but you can be on the lookout in MathLab for those instructions. They will always tell you what to round to. Now, of course, our calculators will do the converting for us as well, so let me show you how to convert between DMS and decimal degrees on your calculator. The button that we're going to need to do this is the third button on the second row, and you can see the degrees, minutes, seconds symbols right there. So this is the button we need. Let me show you what happens when we press this button. So if you press it, you get a menu, and you'll see here the symbol for degrees, minutes, seconds, and then there's an R, which stands for radians, and we will talk about radians later. And then there's a G, which stands for gradians, which is something that we will not use. And then there's an arrow that points to the right. Now that indicates that there is a second screen to this menu. You can access that second screen by arrowing all the way across, and it will flip to the second screen. Or guess what? Because there are only 2 screens, you can simply hit the left arrow one time and access that second screen of the menu. So it's your choice. Scroll all the way across to get to the second screen, or just scroll to the left once to get to the second screen. Okay, so now what we're going to do is enter 74 degrees, 8 minutes, and 14 seconds into our calculator. So let me get back to a clear screen, and we'll enter 74. Now I need to tell the calculator that the 74 is degrees. So I'm going to hit the degrees, minutes, seconds button. Notice that the degree indicator is already underlined, so now I press equal, and you can see the screen displays 74 degrees. Now I can enter the 8 minutes, so 8, hit the degrees, minutes, seconds button again, arrow over so that the minutes symbol is underlined, and press equal. And then we want to enter the seconds, so 14 seconds. Arrow over so that the second symbol is underlined, and press enter or equal. And now your screen displays 74 degrees, 8 minutes, and 14 seconds. And to do the conversion, all you have to do is press the equal button, and it automatically converts to decimal form for you. And as we talked about before, if we want to round to the nearest thousandth, that's going to be the 3rd decimal place. So we look at the 4th decimal place to decide whether the 7 stays a 7 or changes to an 8. And so this 2 is not big enough to make the 7 change to an 8. And so just like before, we end up with 74.137 degrees. Now for part B, we need to start out in degree mode. So you probably already are in degree mode. You'll notice this little DEG indicator in the lower right part of your screen, and that's telling you that if you enter a number and don't tell the calculator what units it is, the calculator will assume that it's degrees. Now, if you do not have the DEG indicator, you'll want to hit this button right here that says DRG, and that will let you change between degrees, radians, and gradians. And so you want to make sure that DEG is underlined so that you're in degree mode. And if it's not underlined, just use your left and right arrows to get the DEG underlined, and then press equal, and you should have that DEG indicator. All right, now to convert 34.817 degrees to DMS form, we're going to go ahead and enter our 34.817. The calculator knows that's degrees because we are in degree mode. And now what we're going to do is use the convert to DMS command in this degrees, minutes, seconds menu. So hit that degrees, minutes, seconds button, and we need to access the second screen of the menu. So remember, you can hit the left arrow button one time to get to that second screen, and then you hit equal to put the command on the screen, and it says it's going to convert 34.817 degrees to DMS form, but we have to hit equal one more time to make it actually do it. And so now you can see that we ended up with 34 degrees, 49 minutes, and 1.2 seconds, just like before. But remember that we always round to the nearest second. And so instead of writing down the 1.2 seconds, I've already rounded that off to 1 second. So 34 degrees, 49 minutes, and 1 second. Now in example 4, we're going to be doing some calculating in DMS form. So it says perform each calculation, 51 degrees and 29 minutes plus 32 degrees and 46 minutes. So if we were going to do this manually, we would do this exactly the same way you would add hours and minutes of time. So we'll put down 51 degrees and 29 minutes plus 32 degrees and 46 minutes. And what we'll do is we'll just add the minutes together and then add the degrees together. So 29 minutes and 46 minutes adds together to give us 75 minutes. And then for the degrees, 51 degrees and 32 degrees adds together to give us 83 degrees. Now we know that this answer is not in final form because we have too many minutes here. There are 60 minutes in a degree, so some of these minutes can be used to make a whole degree. In fact, 75 is 60 plus 15, so 75 minutes is 1 degree and 15 minutes. 60 of our minutes make this 1 degree. So now, instead of 83 degrees and 75 minutes, let's combine the 83 degrees with the 1 degree, and we'll have 84 degrees and 15 minutes. For part B, we have 90 degrees minus 73 degrees and 12 minutes. Now at first you might think, how are we going to subtract 12 minutes because we don't have any minutes over here to take away 12 minutes from. So the trick on something like this is to take one of your degrees and break it into minutes. The same way you would if you had to make change for somebody. If you had only dollar bills and somebody needed quarters, you would break one of your dollar bills into 4 quarters. Well, we'll do the same thing here. We'll break one of our degrees into 60 minutes. So 90 degrees becomes 89 degrees in 60 minutes. It's still worth 90 degrees, it's just one of our degrees is now written in minutes. But this makes it easy to subtract 73 degrees and 12 minutes, because 60 minutes minus 12 minutes leaves 48 minutes, and then 89 degrees minus 73 degrees leaves 16 degrees. So we have 16 degrees and 48 minutes. And of course we can do these operations on the calculator as well. So what I'm going to do is go ahead and enter my 51 degrees and 29 minutes. You already know how to do that. And then plus 32 degrees and 46 minutes. And you'll notice when we press equal, the calculator returns the answer in decimal degrees. But if you really need the answer in DMS form, you know how to convert to DMS form. So you're going to hit the DMS button, scroll left to access that second screen, and then hit equal to get the command, and then hit equal one more time to run the command. And the same thing for part B. We'll enter 90 degrees. And now notice that I don't really have to use the degrees, minutes, seconds button here to tell the calculator that this is degrees. Because we're in degree mode, the calculator knows that that 90 represents 90 degrees. So really, I only have to add the degree symbol if I need to differentiate between degrees and minutes, because the calculator assumes that I'm entering degrees. So now I am going to enter minus 73 degrees and 12 minutes. And of course, when I hit enter, we get our answer back in decimal degrees, and so we'll convert to DMS form by using the degrees, minutes, seconds button, left arrow to get to the second screen of the menu, then hit enter to get the command, enter to run the command, and we get the same answer that we got when we did it by hand, which is 16 degrees and 48 minutes. Now let's talk about standard position. So an angle is in standard position if its vertex is at the origin and its initial side lies along the positive x-axis. And then the terminal side can just fall wherever the terminal side falls. It might be here, or it might be here, or it might be here. It could fall in any quadrant. A standard position angle that's more than 0 degrees but less than 90 degrees will have its terminal side land in quadrant 1, which is the upper right quadrant. A standard position angle that's more than 90 degrees but less than 180 will have its terminal side land in quadrant 2. A standard position angle that's more than 180 but less than 270 will have its terminal side land in quadrant 3. And a standard position angle that's more than 270 but less than 360 degrees will have its terminal side land in quadrant 4. So I know that you probably are already familiar with the quadrants, but make sure that you know that quadrant 1 is located in the upper right of the coordinate system, and then we continue counterclockwise to number the quadrants. So here's quadrant 1 to the right and then up, where all the x coordinates and all the y coordinates are positive, and then continuing counterclockwise, then we have quadrant 2 in the upper left, quadrant 3 in the lower left, and quadrant 4 in the lower right. Now, if the terminal side of an angle falls on the axis, then the angle is not considered to be in a quadrant at all. Instead, these angles are called quadrantal angles, and I've drawn one for you here. So we know that whenever we're talking about standard position, which will be the case all of the time throughout this course, as long as we have a coordinate system in view, we're going to be using standard position angles. So we know that the initial side is here at the positive x-axis, and in this case, the terminal side falls on the positive y-axis, and so this is what's called a quadrantal angle. This angle is not in quadrant 1 or quadrant 2. It's kind of between them, so we just call it a quadrantal angle. Because each quadrant contains 90 degrees, each quadrantal angle is a multiple of 90. So some examples of quadrantal angles include 90 degrees, 180 degrees, 270 degrees, and 360 degrees. And we could keep going. You just keep adding 90 to get to the next quadrantal angle. Now we'll come back and talk about quadrantal angles a lot more in a later section, but for right now let's go ahead and skip to coterminal angles. So two angles with the same initial side and the same terminal side, but different amounts of rotation, are called coterminal angles. So here I've drawn an angle in standard position, and you can see that the terminal side falls in quadrant 2, and this angle is going to be between 90 degrees and 180 degrees because it's just rotating from here around a quadrant 2. So we know it's more than 90, but we know it's not quite 180. However, imagine an angle that has its initial side and its terminal side in the same position, but instead of just going from the positive x-axis to this terminal side, it goes all the way around the coordinate system and then back to that stopping place. And so this angle would be 360 whole degrees plus however much rotation we get from here to here. So these two angles have their initial and terminal sides in the same location, but they are not the same angle because the blue one has more rotation. It goes around the coordinate system one whole time plus some. So here's example 5, and this says find the angles of least positive measure that are coterminal with each angle. So sometimes we want to be able to sketch an angle, and we're really just interested in knowing what quadrant that terminal side falls in. We don't necessarily care how many times the angle goes around the coordinate system. We just need to know what quadrant to draw the terminal side in. So we will always want to know the smallest positive measure of an angle that is coterminal with the angle that we have. And in order to find that smallest positive number, what you do is either subtract 360 degrees or add 360 degrees, whatever you have to do to get to something that's between 0 and 360. So in this case, I'm starting with an angle of 908 degrees. So if I subtract 360 degrees from that, I get 548 degrees, which is also coterminal with 908, but it's not the smallest coterminal angle because this is still large enough that I could subtract 360 a second time, and that gives me 188. Now you can see that if I were to subtract 360 again, I would get a negative answer. So this is the smallest positive measure that is coterminal with 908. And now that I have this information, I would know that if I wanted to sketch this angle, that terminal side would have to fall in quadrant 3. Now let's look at part B. So if we start with an angle of negative 75 degrees, then in order to find the smallest positive number, we'll have to add 360 here. So negative 75 degrees plus 360 gives us a positive answer of 285 degrees. So now we know that negative 75 degrees is coterminal with 285 degrees. It's just that this one is negative, so it has clockwise rotation, and the 285 is positive, so it has counterclockwise rotation. So now let's look at part C, and we're going to start with negative 800 degrees. So we know that to arrive at the smallest positive number, we're going to have to add 360 to this. So negative 800 plus 360 gives us negative 440. That's still not positive, so we'll need to add another 360, and that gives us negative 80. And that's still not positive, so we'll add 360 degrees one more time, and that gives us a final answer of 280. So now we know that an angle of negative 800 degrees is coterminal with an angle of 280 degrees. And this one would be easy to sketch, whereas the negative 800, not so much. Okay, now let's switch gears just a little bit. So still working with coterminal angles, sometimes we want to be able to write a little formula or a little expression that somebody could use to calculate all of the angles that are coterminal with some other known angle. So to find an expression that will generate all angles coterminal with a given angle, all we have to do is add a multiple of 360 degrees to the given angle. But it needs to be a whole multiple of 360 degrees. So the way to get a multiple of 360 is to multiply 360 by an integer. Remember from algebra, an integer is a positive or negative whole number. So like positive 2, positive 3, positive 4, etc. Or it could be negative, negative 1, negative 2, negative 3, negative 4. Those are all integers. What we don't want to do is allow somebody to multiply by a decimal number or some number that's not an integer, because that would not give you that whole rotation all the way around the coordinate system. So if you wanted to write an expression for all angles that are coterminal with 60 degrees, what you would do is start with 60 degrees and then add 360 times n, where n is any integer. And that's it. So you see somebody could plug in any integer value they wanted for n, and they could do, say, for example, 60 degrees plus 360 times 2, or 60 degrees plus 360 times negative 5. Whatever integer they plug in for n, that's going to give another angle that is coterminal with 60 degrees, because all the 360n does is add a whole rotation from that 60 degree position. Okay, let's do another one. Suppose we wanted to write an expression for all angles that are coterminal with 225. So we would start with 225, and then we would just add plus 360 degrees times n. So the 225 degrees determines the location of the terminal side, and then the plus 360 degrees times n just tells us that we can go from there any whole number of rotations that we want and find a coterminal angle. Okay, so that's the end of our examples for section 1.1, so you may be wondering what's next. Well, you do have MyLab homework for this section and for every section posted in Canvas. If you're taking our class either online or if you're taking my traditional class on campus, then you will have MyLab homework for every section posted in Canvas. So you'll want to do the section 1.1 homework as soon as you can. Now that you've watched the videos and gone through the examples, don't waste time. Go ahead and do the homework while it's fresh on your mind, and that will be easier for you. Don't procrastinate. Procrastinating is what gets people in trouble, especially in online classes. So what you want to do is plan a study time to do your homework after each video or after each class on campus. Be purposeful. Make time and make a habit. Don't try to fit trigonometry into the cracks. It won't fit. Don't just say every week, well, I'll get to it sometime. I'll see when I can get to it. No, don't do that to yourself, because trigonometry will not fit in the cracks. You have to be intentional, and you have to set a time to get it done, and that way you'll be able to get it done. Good habits lead to good results. If you let things pile up, it can quickly become overwhelming. So do it a little bit at a time. Try to do a little bit every day. It's like exercise. A little bit at a time is good for you. Too much at one time will just make you tired and not get you any results. So do it a little bit along the way. Ask questions whenever you need to. And I'm looking forward to working with you guys. If you are in one of our online classes and you get stuck anywhere along the way, be sure and reach out to your instructor for help. You can contact your instructor in Canvas or use the Ask My Instructor button in MyLab, and we will be glad to help you. So good luck, and I'll see you in the next section. Bye-bye.